Okay, so in this video, I'm going to be talking about the idea of work as a dot product. And a dot product is basically a way of multiplying two vectors. Um, the other way of multiplying two vectors is what's called a cross product or vector product that we'll probably talk about later this year. But today we're going to be talking about dot product. And dot product calculation is really easy, but there are a few questions on your quest homework which requires you to know some of these concepts. Okay, so basically, let's just kind of review. The equation for work, I believe you're given looks something like W equals FD cosine theta. Now, in the last video that you watched, I believe I wrote this Fs cosine theta. That's because in IB physics we use S for displacement instead of D, um, but I believe OnRamps physics uses D instead of S for displacement. In either case, F is the force acting, D is the displacement of the object as it moves. Notice though that force and displacement are both vectors. Work is not a vector. Work is actually a scalar. And so you might wonder, like, how is it possible to multiply two vectors and end up with a scalar, right? How do you multiply two things that have direction and end up with something that does not have direction? And the answer to that is basically the dot product. Okay, and so um, what we're doing here is we're multiplying force and displacement using a dot product, and we're ending up with work. Um, and so today we're going to be looking at what those calculations look like mathematically. Now, normally you would maybe learn about this in pre-calculus, depending on how the pre-calculus course was taught. And so this is just kind of pure math that we're going to start off with, but we will do some examples worth of work by the end of this video. Okay, so let's start with the basics of how a dot product works. The basic idea of a dot product is that, well, before we get to the actual calculation itself, let me just kind of rewrite what you see here. Um, on the left side of this equation, we see vector A, we see a dot, which is why this is called a dot product, and we see B. Okay, so imagine we have two vectors, vector A, vector B. Theta is the angle between those two vectors, right? This left side here, this is a dot product. And on the next slide, we'll talk about how you actually do that calculation. What you need to know, though, is that dot product is equal to, sorry, let me move this around, is equal to the magnitude of vector A. Remember, we use these absolute value bars to represent the magnitude of a vector, times the magnitude of vector B, times the cosine of the angle between those two vectors. Okay, and just to kind of refresh, remember when we talk about the magnitude of a vector, given the components of a vector, um, you can find the magnitude of the vector using the Pythagorean theorem. And so in some problems, you'll be given the components, and in some problems, like a lot of the examples we did with work before, you were just given the magnitude of the force and you were given the magnitude of the displacement. But in other problems, you're given them in component form. Okay, so we'll talk on the next slide about how to actually do the left side of this equation, the dot product side, but it's important that you understand that the dot product is equal to this quantity as well. And so one of the things you can do with a dot product is you can actually use it to find the angle that exists between two vectors. Okay, and you can do so using this equation right here. A dot B, we haven't talked about how to actually do a dot product yet. We'll do that on the next slide. But to find the magnitude of A and to find the magnitude of B is not difficult, and that's something you should be able to do now, because remember, the magnitude of vector A would just be the square root of ax squared plus ay squared, where ax and ay are the components of vector A. And likewise, the magnitude of vector B would be equal to the square root of bx squared plus by squared. Okay, and we've done that in past units where we found the magnitude of a vector given the components. Okay, so that's just to get us started. Okay, so on the next slide, we'll talk about how do you actually do the left side. What does a dot product calculation look like? It's actually not difficult at all, and then we'll do a few basic examples. Okay, so make sure you have that in your notes. Okay, so how do you calculate a dot product? Okay, so you can add this to your notes as I write, but imagine we have vector A and vector B, and let's say vector A has components AX. Um, I was about to write X hat. I'm actually going to write J hat just because I think you have a few problems on your homework where they have I hat, J hat, K hat instead of X hat, Y hat, Z hat. It's all the same thing. Okay, but imagine we have vector A, and vector A has components that look something like this, and vector B has components that look something like this. And understand that what I'm writing right now is exactly what you see up here. It's just written in a different form, right? Up here is just vector notation, and down here I'm using unit vector notation, but to represent the exact same information. Okay, so imagine I've got two vectors, vector A and vector B. How do I do their dot product? Okay, well, it's actually very simple. The dot product, in order to do the dot product of A and B, all you do is you multiply the x components together plus the multiplication of the y components. And if you had z components, you would add those in as well. And that's it. Okay, it's a very simple calculation. So basically, if you have it written like this, it would basically just be this times this plus this times this. You multiply the x's together, you multiply the y's together, you add those two numbers together, right? Because at that point you have a number, you have a scalar, you no longer have a vector. And that's how you did dot product. Okay, very simple. Okay, so pause there, make sure you add that to your notes, and then we'll do some examples, and hopefully you find this pretty simple. Okay, so simple example. We're going to start off with just pure math, and then we'll do some work examples on the next slide. Two vectors A and B are shown with their components below, and we're asked to calculate the dot product between these two vectors and then calculate the angle between the two vectors. Okay, so the first thing we want to do is we want to do A dot B. Okay, and remember, to do a dot product, all I'm going to do is I'm going to multiply the x components together. So in this case, I would do 3 times -5 plus, then I multiply the y components together, 4 times 12. 3 times -5 is -15. 4 times 12 is 48. And so that's going to be a positive 33. And that's the answer to the first question. Okay, that is the dot product. That's it. Notice, by the way, again, we start with two vectors and somehow we end up with a scalar. That's just how dot product works. Okay, so the dot product between these is just 33. Now, the second question asks us to calculate the angle between the two vectors. And remember, the equation is A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay, so we know that A dot B is 33. So let's find the magnitude of A. And so the magnitude of vector A, given these components, would be the square root of AX, which is, 3 squared, plus AY, which is 4 squared, and that would be 5. And so vector A has a magnitude of 5. And likewise, we could do the same thing for vector B. That would be the square root of -5 squared. Make sure you put the parentheses around the negative because otherwise it's going to do 5 squared and turn it negative, which is not what you want. The negative sign should cancel out when you square this here. Okay, so plus 12 squared, and we actually get 13. Okay, and so if I go back in and I plug into this equation, on the left side here, this is the equation I'm plugging into. On the left side, I have 33, that's just the dot product. The magnitude of A is 5. The magnitude of B is 13 times cosine theta. And then just to finish this off down here, theta would then be the inverse cosine of 33 divided by 5 times 13 is 65. Okay, so I'm going to double check to make sure that my calculator is in degree mode before I type this in, because otherwise you might get the wrong answer if your calculator is in radian mode, and that would be bad. Okay, so I'm going to do inverse cosine of 33 divide by 65, and that is going to give me an angle of 59.5 degrees. Okay, and so that is the angle between these two vectors. Okay, so pause it there, make sure you add that to your notes. All right, so let's do a few quick examples with work, and then we will be done with this short video. Okay, so um, this example actually, so this example says a constant force with components given by F equals 4i hat plus 2j hat acts on an object and causes it to move with a displacement given by D equals 5i hat plus 0j hat. And the first question says calculate the work that this force does on this object. Okay, so remember, work is FD cosine theta. If you actually draw these vectors out, you'll see that this one is going at an angle with the positive x direction, and the displacement is only in the positive x direction. There's no y component to that. Okay, so you can imagine, for example, like a box is being pulled like at an angle by a rope, but it's only moving horizontally because it's being pulled along like the a flat surface. Okay, so that could be the situation that you have here. Okay, now remember that on the left side here, really what we have is we have the dot product of F and D. Okay, so really what we have is we have F dot D is equal to the magnitude of F times the magnitude of D, oops, times cosine theta. Okay, so if I want to find the work done, that work is just equal to the dot product of force and displacement. Okay, and that's actually how a lot of textbooks write it. They write it like that rather than writing the FD cosine theta. Okay, so the work done, I would need to find the dot product between F and D, and I can do that based off of what we talked about on the last slide. So remember, to do a dot product, all you do is you multiply the x components together and the y components together and add them together. And so the work here would be, so let's see, the x component of F would be 4. The x component of D would be 5. So 4 times 5 plus, now we multiply the y components, 2 times 0, which is just going to be 0. And so the work done here is going to be 20 joules. All right, now what if I want to find the angle between the force and the displacement vectors? Okay, so to do that, I would need to find the magnitude of the force, which would be the square root of 4 squared plus 2 squared. Okay, so that would be, let me see, 4 squared is 16 plus 4, so square root of 20 would be 4.47 newtons. And then the magnitude of the displacement, I would do the square root of 5 squared plus 0 squared, which is just 5 meters. Okay, and so to get the angle theta between the two, I would do cosine theta is equal to the dot product, which is 20, divided by the magnitude of F, which is 4.47, times the magnitude of D, which is 5. And then I would just do the inverse cosine to get the angle. Okay, so pause it here. Try to see if you can do this calculation on your own, just to make sure you can type it into the calculator correctly. All right, and so the angle you should come up with is 26.5 degrees. Okay, so that's the answer to the second question. So hopefully that's what you got. Pause it there if you need to look at that some more. Okay, and then one final question. This one is actually from your quest homework. Okay, so if you want to pull your quest homework up, that might be helpful for you. But this question says a force F, given by F equals Fx I hat plus Fy j hat, acts on a particle that undergoes a displacement of S. See, here they use S for displacement. They're not really consistent, it seems. given by a displacement of s equals sx I hat plus sy j hat, and then they give you the values for the components. And this question is basically the same as what we saw on the last example. Okay, the work done is equal to the dot product between the force and the displacement, okay, which is also equal to the magnitude of the force times the magnitude of the displacement times cosine theta, where theta is the angle between those two vectors. Okay, so work is equal to both of these things. But in this case, because we have F and S given in component form, it makes the most sense to just do the dot product to find the work done. Okay, so to find the dot product, I'm going to take the X components, multiply those together. Okay, so that would be 10 times 6, plus then the Y components, multiply those together, -5 and 2, and that would be, let's see, 60 and -10 would be 50 joules. Okay, so 50 joules of work is done by this force. And then to find the angle between F and S, I have the dot product, which is 50, and that's equal to the magnitude of F times the magnitude of S times cosine theta. So I need to find the magnitude of the force. That would be the square root of, let's see, 10 squared plus -5 squared. And then the magnitude of S is going to be the square root of 6 squared plus 2 squared. Okay, and so I'm going to go ahead and do that in my calculator. Let's see if you can get this answer correct. All right, so I think I typed it into my calculator wrong. Give me just a second. There we go. Okay, so 11.2 newtons is the magnitude of the force, and the magnitude of the displacement is going to be the square root of 40, which is 6.3 meters. Okay, so 50 equals 11.2 times 6.3 times cosine theta, and then we divide to get cosine theta by itself. We do the inverse cosine to get the angle, so that would be the inverse cosine of 50 divided by 11.2 times 6.3. And let's see, 50 divided by 11.2 times 6.3 inverse cosine. Okay, that's 44.9 degrees. Okay, now do keep in mind that this is a question on your quest homework. Your values obviously might be different. Do make sure that you don't round until the very end. I actually did a bad job of rounding. I probably should not have done that, and so maybe don't round quite as much as I did, because sometimes the quest homework is kind of finicky as far as, how many decimals you have to have and how close it has to be in order to grade it correctly. Okay, so maybe don't round quite as much as I did until the very end, but hopefully that lets you do a couple of the problems on your quest homework. So, as always, please let me know if you have any questions, and I will see you guys in the next video.